We'll start in a minute. Could you guys introduce yourselves? And then we'll start. Uh,
Hello.
yeah, please.
Yes.
Yes.
So I'm Jagdish, currently a third year bachelor's in ECE from Manipal Institute of Technology. I primarily took up this course just to like understand the physics aspect of semiconductor devices.
Okay.
Thank you.
Thank you. So I guess I got the chat message. Hello, sir. Myself, Preet Kumar from Gujarat. Do we get access to the recordings of the sessions? Yes, I mean, you will be provided the recordings as well as the slides for this session. And what about others? Two people introduced. Ajay Kumar, would you introduce yourself? I mean, a brief background of what you are currently studying so that I could get an idea about my audience. Okay, what about the second one? Gagana GV. What about you? Could you introduce yourself? Or anyone, I mean, not necessary to follow the order. Anyone among you? I mean, if you are reluctant to switch on the audio, you can just type in the chat. And I think. Okay, you guys can type that introduction in the chat and I'll start the session. So welcome everyone. This is the first live session of the course NPTEL NOC25 EE-39. The course is titled Fundamentals of Semiconductor Devices. And as you all know, the instructor for the course is Professor Digbijayan Nath. And I'll be the teaching assistant for this session. Probably you have two other sessions as well, problem solving sessions apart from mine. So in this session, I'll be the TA and the schedule for my sessions would be every Sunday, 3 p.m. to 5 p.m. Okay. And if I mean, if I feel that due to some work I need to change the timing for the session, I'll try my best to notify you as early as possible. So these are my contact details in case you want to reach out to me after this session, the email ID and the website. Okay, let's quickly go through the guidelines for this session. In case you have any query, during the session, you can either raise your hand or you can ask in the chat window. And please make sure that your microphones are muted when you don't intend to speak. I mean, you can switch on your microphone when you do intend to speak something or ask any question. But when you don't intend to speak anything, please make sure that your microphones are muted so that there is no noise. And I'll try my best to make it an interactive session because this is supposed to be an interactive session, right? It is supposed to be a live interactive session. And for that, I would need your cooperation as well, right? And please make sure that you have pen and paper handy along with a calculator. If you don't have for this session, make sure you have it ready from next session onwards. Fine. And as I just mentioned, the session recording link and the lecture notes will be shared by the NPTEL course team in the due course of the time. So what are the prerequisites for this session? Prerequisites include the last week's lectures, which covered the following topics. So we started with the introduction to the semiconductors, and then we were introduced to energy bands, and then we learned about the fundamentals of band structure, and then uh, we learned Fermi-Dirac distribution and density of states, right? These were the concepts that were discussed. So I assume that you all have already gone through these topics. By the way, can anyone let me know, do you have assignments as well for this course? I hope so. Anyone can unmute and just let me know. Okay, yes. So you do have assignments. Has that assignment been posted on the platform? I mean, okay, thank you. So, I mean, the plan for this session would be following. I'll be showing you some 5 to 6 problems, right? Which will be followed by 3 to 4 harder problems, and which I expect you to solve live, right? You are free to discuss. I mean, you can unmute yourselves and discuss among yourselves. I won't be assisting in those 3 problems. And once this session is over, we can communicate on mail and then discuss the queries regarding that. Is that fine? And I hope I was clear. Okay. 5 Feb is the last date for the submission of the assignment 1 and 2. Okay, so 2 assignments have already been posted. Fine. So let's start with the first question. We'll start with an easy one. You have to state which band will result in heavier electron effective mass. Would it be band A or band B? I expect most of you to answer this one. So please uh, start answering it. You have to say which band would result in heavier electron mass. Sorry, heavier electron effective mass. Would it be band A or band B? Okay, I got band A, band B, band B. So we have 2 votes for band B and 1 vote for band A.
Band B, sir.
Okay, B. Anyone else who would like to answer it? Should I wait or just show the solution? The solution is straightforward though. Okay, since this one is relatively easy, let me do one thing. Who will be willing to uh, discuss the solution? I mean, I'll write on his behalf, but he should be able to, I mean, direct how the solution to this question is. Anyone who is willing to volunteer for that? The answer is band B. I mean, I'll let you know beforehand. So it's not band A, it's band B. But why is that the case? Okay. So we have the relation that effective mass is inversely proportional to the band curvature, right? And it's given by this m star that is equal to h bar square by d2e by dk square, right? We know this relation, right? So we need to, find uh, this curvature magnitude for the two bands. So the band which will have this magnitude of the curvature less would result in heavier electron mass, right? Because effective mass is inversely proportional to it. So it's quite clear that your d2e by dou 2e by dou k square for band A, right? For band A, this curvature is larger, right? Compared to the curvature for band B. So your m star A would be less than, you can switch off your video. Your m star A would be S Muruga. I'm talking to you. Would you switch off your video? This would save the bandwidth, right? Your m star A would be less than m star B. So thus, the heavier electron effective mass would correspond to band B, right? So the answer is band B, right? As some of you rightly pointed out. Is this fine? Should I move to the next one? This was very easy. Should I move to the next one?
Yes, sir.
Okay, thank you. So the next one is how do you define the Brillouin zone? So which among the following four options uh, correctly describes or defines the Brillouin zone? Let me see the chat. Okay. Would this option be right? Another name of, for the unit cell of the crystal? No, right? I mean, I'm going to discard some options. Okay. So it cannot be C. Okay. Someone said it's A, which is actually the right answer. But I would discard three options and get to A. But yeah, someone correctly answered it. So Brillouin zone is a region of K space which contains all the unique solutions of the wave equation, right? Your EK solutions, the solutions of the energy values corresponding to your K points. So it's a region of K space, right? It's not a position, it's not a region of position space. That's why this is discarded. This I already said, and it's not energy space that contains allowed energy values. So only correct option is this one, A. So we'll take this and proceed to the next one. So this, I guess you already would have seen, right? These diagrams. Uh, this one is the reduced diagram, right? And this one is how it actually looks, right? Your energy values corresponding to various range of K values. Is this fine? I'll move ahead. Now, what about this? Those of you who have pen and paper handy, work it out. Okay. Uh, you need to consider a semiconductor whose energy dispersion relation E of K for the conduction band is defined by E, which is given by A plus B times K minus C whole square. Right? Your A, B, and C are constants. You have to assume the mobility of electron is mu naught. Find the mean free time of electrons in the conduction band. Please work it out. Is anyone willing to discuss how should we approach this question? We need to find the mean free time of electrons, right? What is mean free time expression that we know? That is your tau, which is equal to Q, sorry, your mu naught is Q tau by M star, right? Here, mu naught is the mobility of electrons, right? That is what I wrote mu naught as. So your tau is M star mu naught by Q, isn't it? So you'll find M star and plug this into this equation, and then you'll obtain mean free time of electrons. How would you find M star? Okay, someone is saying C squared. Just a second. Yes, the C is the correct answer. So see what we did. We knew this expression, right? Your M star is h bar square whole divided by dou to E by dou K square, right? And your E is A plus B times K minus C square. What is dou E by dou K? Your dou E by dou K would be 2B K minus C, right? And then we'll take the derivative again, right? Dou to E by dou K square. What is that? Would be 2B, right? Is it clear how this came apart? Type yes in chat so that, I mean, I get to know that you all are following.
Can you explain about like how did we like the mobility equation, like the formula for the mobility?
Okay, so I assume that you already knew this equation. Have you come across this equation? You're not
Uh,
given by
no, I
Q tau
haven't.
by M star. Okay. I mean, okay, fine. If you have not seen, I mean, one intuitive understanding of this equation I could give you is mobility. You could intuitively feel that mobility would be inversely proportional to effective mass. Would you agree with me on that?
Yeah.
And then consider these two to be the constant of that inverse proportionality. Okay. There is, I mean, there would be, I guess, a derivation for that. I'm just telling you a plain and intuitive argument to explain this.
Okay.
Okay.
Yeah. Fine. Yeah.
Okay. So yeah, once we get this d2 dou 2e by dou k square, which we got 2b, we can plug this into this equation and we get following. We get that tau is equal to, okay, wait, your m star, wait, let's first write m star, right? Okay, let's see. See, our m star would be h bar square whole divided by 2b, right? And our tau would be h bar square mu naught whole divided by 2bq. Wait, yes, it's 2bq. Is it clear? I evaluated this m star and then I plugged it into this equation to get this mean free time, because this is what I was supposed to obtain. Okay. If no one has any question on this one, so we could move ahead. Yes. This one I want you all to try out. First, you guys would try, and then I will chip in. So you need to consider the following energy dispersion relationship for a charge carrier in a periodic crystal lattice. Your E of k is equal to 2 sine square k. The expression for effective mass m star is. H bar square by 4 cos of 2k. Yes, somebody answered it in the chat, and that is the correct expression that even I got. So I just wait, write this that everyone is able to follow. Your E of k is equal to 2 sine square k, right? You know that my m star is equal to h bar square by dou 2e by dou k square, right? I know this one. Now, your E of k would be equal to 1 minus, yeah, I can write this as 1 minus cos of 2k, right? Mathematical manipulation. See, because your cos of 2k, that is cos square k minus sine square k, right? And cos square k can be written as 1 minus sine square k, right? So you have 1 minus 2 sine square k. So 2 sine square k can be written as 1 minus cos of 2k. Is this clear? So if I'm able to write it like this, then it's matter of differentiating. So dou E by dou K would be equal to, if you differentiate this, you'll get 4. I mean, I can directly differentiate it 2 times to get 4 cos of 2K, right? And then your M star would be H bar square whole divided by dou 2E by dou K square, right? So this would be H bar square by 4 cos of 2K, as was mentioned in the chat by 2 people, right? Is this clear to everyone now? Okay. Now let's consider this one now. This one would, I mean, I guess, need more math than the previous questions. So you need to assume, uh, I mean, is everyone fine with the first 4 questions now? Moving ahead. Just let me know if I'm moving too fast. I mean, slow my pace down. Is the pace fine to everyone? Okay, thank you. So now assume that silicon, which has a band gap of 1.12 electron volt at room temperature, 300 Kelvin, with a Fermi level located exactly in the middle of the band gap. You need to answer following questions now. What is the probability that state located at the bottom of the conduction band is filled? A is 0.5. How come? 1. No, it's neither 0.5 nor 1. See, it's not 0 Kelvin, right? It is at a temperature, right, of 300 Kelvin. That's why, no, 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 no. It's not 0, neither 0 nor 1. Okay, let me show you how. Can proceed on this one. Should I end the page? See, your f of e is equal to 1 by 1 plus exponential of e minus ef by kt, right? Everyone knows this Fermi function. Okay. So, and for our problem, your this e, right? This e would be your bottom of the conduction band, that is EC, right? So we'll compute f of EC, right? What is your f of EC? See, for our problem, E is equal to EC. So your f of EC would be equal to EG equal to KT. G equal to KT. I will see. See, your f of EC would be equal to 1 by 1 plus exponential of, I'll replace E by EC, right? So it would be EC minus EF by KBT. It's understood. Your K is that Boltzmann constant, okay? So now, can we approximate it like this? Can I use this approximation? What have I assumed? In order for me to write this as this, what is the approximation that I have made? Can someone unmute and let me know?
Here exponential term is much higher than 1.
Yeah,
So
exactly.
1.
Yeah, I got the answer. So the approximation that I have made is this term is much greater than this one. And when would that be true? That would be true when your EC minus EF is sufficiently large, right? Your EF is sufficiently uh, away from your EC, right? Only then this difference would be large and consequently this value of the exponential would be large. Is this clear? Okay. So now that is in fact said to be a non-degenerate semiconductor, and uh, your bottom of the conduction band is very far above this Fermi level. Okay. And what about EF? Wait a second. Where is our EF located? Our EF is located exactly in the middle of the band gap, isn't it? See, your Fermi level located exactly in the middle of the band gap, right? That is what was given in the question, right? So what can I write for EF in terms of EC and EV? Please try to answer this one. Is the question clear? Yes, no, any answer?
EV by 2 is EF.
You were not audible. Could you come again?
Yeah, it's EF minus EV by 2 is EF.
Yeah, EC plus EV by 2. I think that is what you meant, right?
Yeah.
Okay. I mean, your voice was breaking. I guess I'm getting the answers. 100% chance to failed 0.56. We'll see. No, they are not correct. See, I guess one of the students tried to answer following. He said EF can be written as EC plus EV by 2, right? Why? Because our Fermi level is exactly in the middle of the band gap, right? Only then can I uh, write it in this fashion. Okay. Now, what is your, this is EF, right? What about EC minus CF? I'm interested in this, right? EC minus CF. What about EC minus CF then? Your EC minus CF would be EC minus EC plus EV by 2, right? And what is that equal to? Yeah, 2 EC minus EC is EC. So it's, I guess, EC minus EV by 2. Yeah, it's EC minus EV by 2, which is nothing but EG by 2. Are you all able to follow it? Okay. This is almost done now. See, choose a different color so that you are able to follow it. We'll get the slides as well. Please make sure you have pen and paper from the next session onwards, because I want you all to work it out before me first. I'll be waiting for you guys from the next session to first work it out. I'll give you sufficient time so that you could learn in the session itself. Okay. So now we know what is the value of EC minus CF. So that is what I'll substitute, right? Here, f of EF, sorry, I mean f of EC, right? This. Your f of EC would be equal to 1 by 1 plus exponential of EG by 2 kT, right? Is this clear? So which is the answer, right? Your answer is you had to compute the probability, which was given by this f of EC, right? So if you put in the values, what is EG? Although you should know this constant, but was provided in the question as well. Your EG is 1.12 electron volt, right? So your EG is 1.12 electron volt. What about this KBT at room temperature? We know that this KT is equal to 0.026 electron volt, right? And EG by 2 kT. EG by 2 kT would be equal to 21.5. Okay, then do one thing. If anyone among you has got calculator, put in the values and let me know what f of EC should be, right? I want you to substitute it into this and tell me what should be the value of f of EC.
It's 4.43 times 10 power minus 10.
Okay, thank you. So this is 4.43 into 10 to the power minus 10, right? This was f of EC, right? And remember, this is no approximation was used, right? I mean, we did not use approximation. What if we had used the approximation, the non-degenerate approximation? Could you plug in the values for this one? For this one, it would be exponential of minus EG by 2 kT, right? Just plug in the values and let everyone know what should be the value.
Probability then 4.6 into 10 to the power minus 10.
4.46 into 10 to the power minus 10. Is that the case?
4.6.
4.6.
Hmm.
No, I don't think it would be 4.6. Can anyone recheck this one? I mean, we should not have a decimal change. It would be 4.4 only, I think. Can someone work it out? So this is what I want you all to compute. This is f of EC for when no approximation is used, right? And this is when non-degenerate approximation is used, right? At that time, your f of EC would be exponential of minus Eg by 2kT. What would be the value? Let's call this prime, okay, or not. What is this value?
We got the same value, 4.43 for the
We got the same value, right? That is what
yeah,
I
yeah.
said. I mean, we should not have a decimal change. 4.43 into 10 to the power minus 10. This is when approximation. In fact, we had separate approximation. I think you were introduced to this term. Was this term non-degenerate approximation introduced? Even if it was not introduced, I mean, keep this in mind, okay? When your Fermi level is sufficiently away from the band edges, that is non-degenerate approximation, okay? So, yeah, I mean, it works. Why does it work? Because EC and EF are sufficiently apart. Try this at your own end. If EC and EF are not sufficiently apart and they are, I mean, close enough that the value of this exponential is comparable to the value of the one, then this approximation fails, right? It won't give you correct answer. You can no longer use this approximation. Okay, this is something that I leave as an exercise for you all. Okay, now we are done with this. Okay, so that is the reason why your answers 0, 0.51, whatever were coming. Somebody said 0.56, all were wrong. This is the right answer. Although it's very close to zero, but it's not exactly zero, right? Is this clear now? Okay, thank you. So now what about the second one? What is the probability that a state that is located at the top of the valence band is empty? Part B. How would we proceed on that one? Okay, before answering this one, can anyone tell me what does, okay, somebody said 1 minus f of v, I was coming on to that one. Okay, let me still build the argument again. What does Fermi function give us? Which probability does the Fermi function give us? Can anyone shed light on that? Probability of find an electron. See, the probability, no, it's not that. I mean, the Fermi function would give you the probability that the state E is full. What is the probability that this state would be full, right? This state would be occupied. That is the probability which this Fermi function would give. Okay, so if Fermi function would give you the probability that this state is occupied, and we know that the total probability cannot exceed one, right? I mean, uh, at max the probability can be one. So right, so the complement of that probability would give you the probability that the state E is empty. Does this make sense? Yes, no? If needed, I can explain it again. Okay, please. Somebody had a question. Somebody raised their hand. You can unmute and please go ahead. Was it accidental or you intended? Okay.
It was accidental.
Okay, it's fine. See, the point that I made was that, okay, this is part B, right? Your 1 minus f of e. Okay, first, let me write what f of e is. Your f of e would be the probability that state E is occupied or say filled, whatever you like. Both mean the same, right? So your 1 minus f of E would be the probability that state E is empty, right? Because we can either have a state that is filled or we can have a state empty. I mean, we cannot have a partially filled state, right? A state, given a state E, either it will be empty or it would be filled. Can you think of any other event apart from these two for a state E? No, right? Okay, somebody said once more. I was explaining. I hope I was clear this time. Vikash Rai. Was this clear this time around? Your Fermi function gives you the probability that your state E is filled. And since there are only two possibilities, right? Either your state would be filled or your state would be empty. So it's quite intuitive to think, even from the set theory perspective, that your 1 minus f of E would give you the probability that your state E is empty. Okay, thank you. I guess everyone understood it this time around. So, okay, let me add a page. Okay, now what about f of E again? I can take it from here, right? F of E was this. Okay, copy and paste it. Right, this is f of E. And for this question, we have been asked about this, right? Top of the valence band. What is that? Top of the valence band? We take that as EV, right? So we'll replace E by EV for this question. So E is equal to EV for this question. Is this clear? But then there was other part of the question that we are now interested in computing the probability that this particular state that is located at the top of the valence band is empty, right? And we know this would give the probability. What would this give? Okay. This would let me know if you guys have understood it. What would f of EV give me the probability? Which probability is f of EV? Can somebody unmute and be clear with an answer? Which probability would f of EV give me?
That the state E is occupied.
that your and E for this case is the top of the valence band, right? So this would give us the probability that the top of the valence band
Valence
state
band is
is
occupied.
occupied. Yeah, that is what f of EV would give you. And what about 1 minus f of EV?
If the
Which
valence
probability?
band, top of valence band is empty.
Yeah, probability that the top of the valence band is empty. And we are interested in the second quantity, right? 1 minus f of E, because 1 minus f of EV, because that is what has been asked, right? We need to compute the probability that state located at the top of the valence band is empty. So yeah, that is how we would proceed. 1 minus f of EV, which would be 1 minus 1 by 1 plus. Those who have calculators available, keep them handy. I'll need your help. So this would be exponential AV minus EF by KT. Right. And now what about, okay, again, like we proceeded in the previous part, our EF was EC plus EV by 2, right? Why? Because it's located in the middle of the band gap, right? And what about now this EV minus EF? What about EV minus EF?
Be minus EG by 2.
It would be minus CG by 2. Yes. Let me work it out. EV minus EF. Yeah, it would be minus EG by 2. Thank you. So now I'll substitute it to this, right? I'll have following. 1 minus f of EV would be 1 minus 1 by 1 plus exponential of minus EG by 2 KT, right? I mean, EG, is 0. Sorry, EG is 1.12 electron volts, right? And what about KT? KT would be 0.026 electron volts, right? Substitute these and let me know the answer.
It's 4.43 times 10 power minus 10. The same value.
4.43 times, yeah, same value.
Yeah.
That is what was expected. Because it's symmetrical, right? I hope you are able to understand. So our 1 minus f of EV was equal to 4.43 into 10 to the power minus 10. And again, even if you had used the non-degenerate approximation, which is valid in this case, right? Because your Fermi level is sufficiently away from the valence band. It's either way around. It should be sufficiently away from the conduction band to use non-degenerate approximation from that side, and similarly from this side. Okay. So even if you had used approximation, you would have come to the same answer, right? So 1 minus f of EV would be equal to 4.43 to 10 to the power minus 10, which means the probability that the top of the valence band state is empty is 4.43 into 10 to the power minus 10. I mean, try to get the feel of how small this number is, right? It's 10 to the power minus 10. It's very close to zero, right? I hope that was clear. So uh, since Fermi level was exactly in the middle of the band gap, uh, the probability that a state at the conduction band edge is occupied was exactly the same as the probability that a state at the valence band edge is empty. The symmetry of the problem arised because of the position of the Fermi level. Had I not placed the Fermi level at the middle of the band gap, try to convince yourself that I would not have obtained the same probabilities. Does everyone feel same? Okay. I guess everyone thinks alike. So it's fine. I mean, we finished this question 5. Question 5 was a good question. So now let's move to the one more good question. Okay. We have silicon at room temperature and we need to calculate the following quantities. Okay. Numerical answers are required and don't forget to include units. Okay, leave that aside. Density of states in the conduction band, Gc of E at energy 26 milli electron volt above EC. Okay, we need to find density of states, Gc of E at an energy 26 milli electron volt above EC. Anyone who is willing to discuss how should we approach the problem? Even a vague idea would do for me. Okay, if no one, okay, I'll start it. By the way, this would be the last problem that I'll show in today's session, and the rest 4 are homework problems for this session. Also, tell me one thing. You guys would have attempted assignment 1, right? How do these problems stand in terms of difficulty compared to your assignment? Are these tougher or is your assignment tougher? Because I did not get time to go through your assignment actually. That's why I'm asking this. From next time onwards, I'll do check your assignment so that I could prepare the problems that are of similar difficulty. So these are a bit tough but interesting. Okay, I guess that is fine. As long as you guys understand it, then it's fine for me. Doesn't matter if they are difficult. Okay, now density of states in the conduction band Gc of E at energy 26 milli electron volt above EC. So first we would write the expression for Gc of E, right? Because I use it. Okay, I already created a page. Okay, this is part A, right? And I need to find Gc of E at energy 26 milli electron volt above EC. Fine. This is how I would write it. I assume you guys would have. I miss problems 1 and 2 you explained today. If you can share them or explain them once again. Okay, so the idea is you guys would get access to the recording and the slides as well. So you can go through those problems uh, in the recorded form as well. But please try to attend the live session because that does help, right? Because the purpose of this session is live interactive session. So although this would be recorded, but still getting idea of your questions and your thoughts is valuable. That's why please try to attend the next session time. Square root of 2 and CC by 5 square h bar cube, right? Have you guys seen this one? This expression? No. Okay. This is the density of state expression, right? The conduction band density of states expression.
Sorry to interrupt.
Yeah.
In the course, we saw a little different equation actually. Like it was
Yeah.
4 pi.
That doesn't. It would be probably your this h bar won't be h bar. It would be Planck's constant h. I'm using reduced
Yeah.
Planck constant. That could be the case.
Okay.
Okay. I understood. Might have. Here h bar is h by 2 pi. And if you substitute that, and you will get this equation. Please do this exercise. Thanks for bringing this to my input. Okay. So this is how you would proceed on this one then. Your GC of E would be, okay. Can I write it in this way? If I take in star common, fine. I'm having mn star raised power 3 by 2, right? Because it's 1 over here and 1 by 2 exponent here. Clubbing them, 1 plus 1 by 2 would be 3 by 2, right? That's why I wrote mn star raised to the power 3 by 2. And what if I do this? Right now, what have I introduced additional into this equation is m naught raised to the power 3 by 2, right? So I need to now multiply the same in the numerator as well, right? This is how I'll do that. M naught square root of 2 m naught, because m naught square root of m naught would be m naught raised to the power 3 by 2. I hope that is clear. If not, you can let me know. And in the denominator, I have that pi square h bar cube, right? And I have this square root of E minus EC. I'll wait for you guys to have a feel of what I did. Is this clear? Okay, understood. So now your m naught here is the rest mass of the electron, okay? And your mn star is the effective mass of the electron. It turns out, I don't want to go that deep, but even effective masses are of two types, right? We have density of states effective mass and conductivity effective mass. And this one, since this is density of states equation, the effective mass that's coming here is the density of states effective mass. If someone is interested in this, he can drop me a mail and then we can discuss from here onwards. I mean, uh, for the scope of this course, you can just consider that this mn star is electron effective mass. Okay. Now I need to put the values, right? Please help me out again. Your GC of E would be, what is m naught? What is the value of the rest mass of electron? this course would have many such problems, such numerical problems. So please try to memorize the value of the constants. Yeah, somebody rightly mentioned it in the chat. It's 9.1 into 10 to the power minus 31, right? Right. Okay. Your m naught is 9.1 into 10 to the power minus 31. What about pi? We know, right? Mm, Pi, you can take the value as 3.14. What else? Your Planck's constant, right? Uh, Planck's constant value h is 6.636 into 10 to the power minus 34 joule second. But this is the reduced Planck's constant, right? You need to divide it by 2 pi. Once you divide that, the value is falling. Your h bar is h by 2 pi, which is equal to 1.06 into 10 to the power minus 34. I hope this is clear and I'm not rushing. Is this clear? Okay, thank you. So, and then also you are supposed to know the following, right? What is the ratio of Mn star to the rest mass of electron? You can check the textbooks for this ratio, or maybe in some other question it might have been provided there, but it's better to learn this as well. The value is 1.18, like 1.18. Okay, so your this effective mass of the electron, right? It is 1.18 times the rest mass of the electron. Okay, and once you plug these values into the above equation, you will get the answer, right? What would you get? This I'll leave as an exercise for you all. Okay, your it's only a matter of plugging them into the calculator. GC of E would be your 1.35 into 10 to the power 56 square root of E minus EC, and the units would be energy per unit energy per unit volume, right? That's why I wrote this, because density of states has that unit. Okay. Now we are asked for the density of states, which is 26 milli electron volt above the bottom of the conduction band, right? So in our case, the E minus EC, what would be E minus EC? See, an energy value that is 26 milli electron volt above EC. Okay, what would be E minus EC for that? It's a simple question that I'm asking.
Electron volt.
26 milli electron volt, correct. So now for this question, E minus EC would be equal to 26 milli electron volt, right? And okay, so now let's convert everything to SI, okay, so that we don't mess with the units. So my E minus EC would be equal to 0.026 into 1.6 into 10 to the power minus 19, right? This would be E minus EC. So which would be equal to, you can work it out. This would be 4.16 into 10 to the power minus 21 joules. Okay. So now we were interested in finding GC, and E in our case would be 26 milli electron volt above EC, right? So let me write that out. 0.026 plus EC. Just correct me if I make any mistake somewhere. And if you plug the value. Which value do you need to plug? This E minus CC. The computed E minus CC is this. If you plug this here, what value would you get? The value would be 8.71 into 10 to the power 45, and the unit would be the same, right? Because density of states has this unit, per unit energy per unit volume, right? Let me write in this fashion instead of this so that it's clear. It's per unit energy per unit volume. And then since when working with semiconductors, we often express energies and what should I say? We express answers per electron volt per cubic centimeter, right? I mean, lot of answers would revolve around electron volt or centimeter cube. I'll leave this as an exercise for you. Work it out how this comes about, right? Your GC just a unit conversion, okay? In terms of per electron volt per centimeter cube, this would be 1.39 into 10 to the power 21, right? Electron volt. Is this clear? Per electron volt per centimeter cube. I mean, the dimension remains same. It's just that I have changed the units now from per joule per meter cube to per electron volt per centimeter cube. I hope it is clear.
I just have a conceptual doubt. So
Yeah, please.
as we go for a higher energy level, so that would indicate that we would have more number of states in per unit energy and per unit volume, right?
Yes.
So actually, like, how is the number of states increasing with respect to energy? Like, can you give some intuition? Like,
How is
number of states increasing with the rise in energy level?
okay. Mm, we'll discuss this over mail. I mean, it would just divert
Okay.
this session right now because uh, these are actually little lengthy parts, B, C, D, and E. That's why
Yeah,
I
sure,
would
sure, sure. Yeah,
want to invest. Just drop me an email and I'll take it from there. Fine?
sure. Yeah, thank you.
Okay, thank you. So now part B is the density of states in the valence band, GV of E at energy 26 millielectron volt below EV, right? This is almost a symmetrical problem. Yes, I would need a different page. Okay, now for part B, we do the following. Okay, I'll write the expression for you and then I would want you to compute it. Now for this, we'll have this MP star, right? Effective mass of hole. This would be EV minus E, and our E would be less than EV. Here it was E was greater than EC, right? Right. And what else? Yeah. And then proceed in a similar fashion like we did for part A, and these are the quantities that I'll give you. You might be needing this one, MP star by M naught. This is 0.81. Okay, you might want to use this one. And then, yeah, you'll get this GV of E as this 7.65 into 10 to the power 55 square root of EV minus E, right? Yeah, per joule per meter cube. Note that this density of states in the valence band is little smaller than in the conduction band, right? In the here it was around magnitude was this, and now we have this, right? The reason is your whole effective mass is smaller compared to the electron effective mass. Okay, that's why this slight change in value comes about. So now we are asked for the density of states 26 milli-electron volt below the top of the valence band. So what would be EV minus E for this case? Let me repeat it. We are asked for the density of states GV of V for state 26 milli-electron volt below the top of the valence band. So what would be EV minus E? 26 milli-electron volt. Would it be? Why do you guys seem okay? I got the thumbs up. Fine. So I hope it's clear to everyone. So now your GV of EV minus 0.026 electron volt would be it's 4.94 into 10 to the power 45 per joule per meter cube, which if you convert to per electron volt per centimeter cube, this would be following. Okay. Yep, done. Is this clear? This is something that you would work it out. Okay. This is just matter of plugging and playing with expressions, which you all are good at. So this finishes our part B. What about part C? Okay, I'll leave this part C and D as assignment. What about E part? Fact, for E part, you need the value of this part C, right? So try these. Okay, part C, D, and E. I want that you should try it out. If you're not able to get the answers corresponding to C, D, and D, write a mail to me and I'll share the solution corresponding to C, D, and E. Okay, but first I want you to try it out. What is this NC? This is effective density of conduction band states. Okay, go through the course content. And one more, I mean, the way I have designed these problems is we started from a basic problem and now we are moving towards much tougher problems, right? So it's okay if you, I mean, feel a little lost as we are going ahead. The idea is not that, I mean, you should be able to solve all of them. It's just that, I mean, you should get a sense of how these problems are in this topic. I mean, I tried to include different kinds of problems. Some of them may be tougher, some of them are easy, so that everyone gets something. Fine. Your party is to compute the ratio of the effective density of conduction band states to the atomic density of silicon. We'll try this part C, D, and E. What else? Okay, then we have our homework problem 1, uh, which uh, is kind of, what should I say, supplementary problems. I mean, uh, till problem number 6 was where the problems that I was with you. I mean, I tried to solve them with you. From next time onwards, uh, uh, our mandatory problems would be tried out by you first, right? You would have a pen and paper with you, and then uh, you'll first work it out, and then I'll see if my assistance is needed. Okay, somebody is saying what will be the format of the final exam, objective or subjective? I actually don't have any idea about that. I mean, please write a mail to NPTEL course team or maybe ask instructor. I mean, or maybe ask in the forum. There would be forum, right? You can write on that as well. Okay, this is your homework problem 1, homework problem 2, homework problem 3, and homework problem 4. You guys would go through these 4 problems and try to solve them, uh, try to solve as many as you can. And keep in mind the level of difficulty in these sessions is way higher than it would be in the exams. So don't get discouraged that, I mean, I showed you tough problems or these homework problems are way tougher. It's just that they are way interesting than those easy problems. I mean, easy problems you would get from many resources, right? That's why I found these problems interesting. That's why I included them here. I hope it's clear. So this would be it, and we'll call it a day. So please try out CD and E first, right? And then delve into this homework problem session. This would be your mandatory homework, and this would be your supplementary homework. It's up to you, optional. If you are highly motivated, you can go through these 4 problems and feel free to discuss with you. If needed, I mean, I can create a group as well for you or use this team chat. See, you can, yeah, I'll share this document and I'll share these slides. So what you can do is utilize this team chat corresponding to my link. When you open my link, there is a team chat, right? And you can write that right in that chat and you can discuss among yourselves. That would be a way you guys are connected for these problems. Please utilize that. Even when my sessions are not going on live, we can still chat. I mean, once I end this session, I'll stop the recording. Still, you guys can chat. Chat would be available 24/7. Okay, feel free to use that and uh, talk among yourselves on that. That fine? Okay. So Should I end the session then? A couple of students had queries. I'll try my best to answer them on email. Okay, please drop me an email,
Sir,
preferably in the first half. Yeah, please go ahead.
this
Please.
recorded is available. Sir, this recorded
I
will be
mean, I'll
available.
provide the recordings. Yes. Recordings will be provided on the by the NPTEL team. Or if you don't get access to the recordings by next Sunday, I'll show you where to see those recordings. But I'm sure you will be, or you can do one thing. Just a second. Let me share my YouTube handle. I'll post it there. Okay, this is my YouTube handle, and I'll be sharing the recordings of this series in a nutshell. There would be 12 to 13 live sessions. You can check this channel later, and I guess probably by the evening I would have uploaded the recording. Is it fine now? Okay. So yeah, the idea is to create a YouTube playlist and add all the videos week by week. So this would be the week one. If there are no more questions, I'll end the session. Thank you for tuning in. Thank you.
Thank you,
And
sir.
please utilize the chat. It would be open even after the meeting ends. You can discuss these problems among you. You all would be connected by this chat. Okay. Thank you. Bye.